Can you guys hear me all right? Hopefully. Hey, Lauren. Samantha's here. Hello. Okay. Maybe I'll give people a few more minutes. Only 7 of you on. Or maybe this is just a low participation review session. We'll see. Any of you guys have anything in particular you wanted me to go over? So far, it seems like the ones who are watching are the ones who don't necessarily really need the review session, but just in case. Yeah, I'll probably go over the answers on the homework for sure. And I usually do that at some point. Lauren, yeah, there's probably explaining about something or other. Maybe about limiting behavior, maybe about whether to use a logistic function. Oh, shoot. Maybe about fitting a logistic curve or an exponential curve, or where a logistic curve would make sense and where an exponential curve would make sense. Those might be explaining things. But I would say, yeah, good chance that there's explaining. The demonstration thing. Yeah, you're going to probably have to prove a property of logarithms, demonstrate a property of logarithms. I hesitate to call them proofs. For sure. That's another form of explaining. Good point, Samantha. Well, I've lost ground from 7 down to 5. So I guess I should better start before I lose everybody. Do you want me to start at the beginning and go through the answers, or is that not really super worthwhile? I could just show you the answers if Samantha just needs the answers. Hey, Jasmine. Finding an inverse function. That sounds like a great thing to do, Rebecca. Let's do that. So the one where you had to find the inverse function that was in the review assignment was on 18. Let's do one of those. That's a great call. So on 18, the function said find the inverse, and it was f of x equals 2 minus x over 3 plus x. And to find the inverse, I'm going to say, okay, this is like y equals 2 minus x over 3 plus x. And then I'm going to switch x and y. So I get x equals 2 minus y over 3 plus y. And now I have to solve the new equation for y. So let's see how to do that. Well, I'm going to start by going ahead and cross multiplying. So I get 3 plus y times x equals 2 minus y. And then I'm going to get 3x plus xy equals 2 minus y. And I want to get all my y's on the same side of the equation to be able to solve for y. So I'm going to say xy plus y equals 2 minus 3x. So just so no one's worried, what happened there was I said minus 3x and minus 3x. And I also said plus y and plus y. And then I'm going to say, let's go ahead and factor out a y. So this is y times x plus 1. And then I'll divide. So now y equals 2 minus 3x over x plus 1. So this is the inverse function. Questions on that? I'm waiting for the lag to catch up. See if you guys actually have any questions. Maybe not. Do we have to graph a logistic function without Desmos? That's a great question. I don't think we've done much of that, so no, I'm going to say no. You don't have to graph a logistic function without Desmos. Jasmine, will this be graphed? Well, we certainly could graph it. I think on this one, it's worth right away showing what it means that it's an inverse function, which would be, if this is on the Desmos section, I'm not saying it necessarily will be, it might not be, but if this is on the Desmos section, we might say f of x equals 2 minus x over 3 plus x. And then we're going to say this other function, which Desmos doesn't understand inverse notation. 2 minus 3x over x plus 1. And we can see that these two functions have symmetry about the line y equals x. And we can see that if we did f of g of x, we'd get the line f equals x. And if we did g of f of x, we'd also get the line y equals x. So it's nice to be able to approach it from a graphing perspective, Jasmine, because that helps us see what inverses mean in a much clearer manner. Now, am I going to make you graph this particular function without Desmos on the upcoming test? Probably not. We just had a test on rationals. That was our last unit. I probably wouldn't, again, make you remember things you learned about rationals. But you should be able to, since that was our last unit, and you should remember things from our last unit. So you should notice that, let me go ahead and turn off all these. For example, in f of x, the green function, we have an asymptote at x equals -3. Make that a dashed line, because if we plug a -3 in the denominator, we would get a 0 in the denominator. You can't divide by 0. And you should also notice that the ratio between the top and the bottom is 2/3, -2/3. So we're going to say there's a horizontal asymptote at y equals -2/3. And again, I'm going to make that dashed. So those would be things we would notice about f of x. Then if we're graphing the inverse function, which I've named g of x here in Desmos, we should notice that there's a vertical asymptote at x equals -1. And that there's a horizontal asymptote at y equals -3, because the ratio between the numerator and the denominator is -3. But again, that's all last chapter's material, so I probably wouldn't have you graph a rational function. I very well might make you find an inverse function from an exponential and then graph both the exponential and its inverse logarithmic function. That could certainly come up. Should we do a problem like that? I think right next to that, we had some exponential ones, like 3 to the x and log base 3 of x in problems 23 and 24. Yeah, 23. Cool. You're welcome, Jasmine. Rebecca, did that make sense about finding the inverse? 23? Should we do 23, Lauren? Is that what you're saying? Okay, so that was 18, 23. 23, we have f of x equals 3 to the x. And g of x equals log base 3 of x. I guess in 23 you're just plugging things in. So I'll do the answers and then I'll talk more about, what else you might need to do. So you should have gotten A was f of 4. So f of 4 equals 3 to the 4th equals, well, 3 squared is 9, 3 cubed is 27, 3 to the 4th is 81. B is g of 9, which is log of 9, which is the number required to raise 3 to get to 9, which is 2, because 3 squared equals 9. On C, you get f of negative 2. So f of negative 2 equals 3 to the negative 2, which is 1 over 3 squared, which is 1/9. And on D, you get g of 1/27th, which is log base 3 of 1/27th. So that's the number required to raise 3 to get to 1/27th, which is negative 3, because 3 to the negative 3rd is 1/27th. Okay, now if we were thinking about from an inverse perspective, so I'm going to kind of put this over to the side. This was the actual problem. This is what they asked you to do. I'm going to say that if we were doing a problem like Rebecca asked about, we might say, find the inverse of f of x equals 3 to the x. I mean, which is the problem here on 23. It might be more complicated on the test. Graph f of x and its inverse. State the domain and range for each. There's quite likely going to be a problem that looks something like that. So in order to do that, we would say if f of x equals 3 to the x, then I want to say y equals 3 to the x. Then I'm going to switch the x and y, so x equals 3 to the y, and solve for y. Y equals log base 3 of x. That's the inverse function. And I should be able to graph by hand, even without Desmos, both of those functions. F of x equals 3 to the x, 3 to the 0 is 1, 3 to the first power is 3. So we've got a function that looks like that. And then the inverse function, which looks like that. So there's f of x and its inverse. So I well might ask you to do that without Desmos. We notice again that when we do that, we have symmetry about the line y equals x. And we would know that f of its inverse equals x, and the inverse of f of x equals x. Domain and range for, I'll do f in blue. So I drew it in blue. For the original function f of x, domain is the set x such that x equals all reals. and the range is the set y such that y is greater than 0. On the inverse function, we should be used to the idea that the inverse reverses the domain with the range. That is just an extension of what we do to find an inverse, which is to flip the x's and the y's. The x's is the domain, the range is the y's. When we flip them, the domain and the range switch. But just to be explicit, domain of the inverse function is x such that x is greater than 0, and the range of the inverse function is y such that y is equal to all reals. So again, just to be clear for anyone who's maybe watching later, this here was the original problem, what the book actually asked you to do. This is only review. This is an additional idea to review for the test. Additional. Book problem. I hope that's clear. Any questions about 23 or the work I just did in relationship to number 23? Do you guys want to do a more complicated exponential and log inverse problem, like what might come up on a test, or should we do other problems from the practice set from the book? Any thoughts? Could we do like a harder exponential and logs problem? Owen, is that what you're saying? Sweet, let's do it. So another, yeah, like what we just did with number 23, we could graph a harder one. Let's check it out. So let's say we have log, oh, I don't want to start in orange. Example. And I think you guys are noticing that these are very much like the example of the first quiz question that everyone got on the quiz that we had with a sub over a week ago. Probably, it's quite possible you could see it again. And let's see, they look like f of x is equal to log base 5 of 2x plus 1 minus 3. How about that? Find f inverse of x and graph f of x and f inverse. State the domain. That was junky D. And range of each. So let's see. I know that y is equal to log base 5 of 2x plus 1 minus 3. And now I want to change x and y. So I'm going to say, what if x were to be equal to log base 5 of 2y plus 1 minus 3? Well, the first thing I would do if I were trying to solve for y now is I would say x plus 3 equals log base 5 of 2y plus 1. Now that I've isolated the logarithmic statement, I can say 5 to the x plus 3 power would be equal to 2y plus 1. That means that 2y would be equal to 5 to the x plus 3 power minus 1. And y would equal 5 to the x plus 3 minus 1 all over 2. So that's f of x. Sorry, f inverse. Okay. You should be able to graph both the log function and the exponential function by hand. The way you want to do that is probably by using inputs and outputs in the inverse function, the exponential one, and then just flipping them to graph the logarithmic one. So I'm going to say in for f of x, here are the x's and here are the y's, which means in f inverse, they'll just be switched. Let's use function notation just to be more clear. X's and Y's are the most clear. Okay, so in the inverse function, which I would like to use first, I can plug in, let's see, I'd like to plug in -5, -4, -3, -2, -1, and let's do 0, which means these are going to be outputs in f of x, -5, -4, -3, -2, -1, and 0. I do that here. -5 plus 3 is -2. 5 to the -2 power is 1/25. 1/25 minus 1 is 24/25. 24/25 divided by 2 is 24/50, also known as 12/25. 12/25. Cool. -4 plugged in for x. -4 plus 3 is -1. 5 to the -1 is 1/5. 1/5 minus 1 is 4/5. 4/5 divided by 2 is 2/5. Over here, -3. -3 plus 3 is 0. 5 to the 0 is 1. 1 minus 1 is 0. 0 over 2 is 0. Okay. -2 plus 3 is 1. 5 to the first power is 5. 5 minus 1 is 4. 4 divided by 2 is 2. Okay. -1. -1 plus 3 is 2. 5 squared is 25. 25 minus 1 is 24. 24 over 2 is 12. And lastly, 0, just so I have the intercepts. 0 plus 3 is 3. 5 to the third power is 125. 125 minus 1 is 124. 124 divided by 2 is 62. I need to be able to make a sketch of that by hand, which just means plotting some x's and y's I just found. So on the original function f of x, 12/25 yielded -5. 2/5 yielded -4. Zero yielded -3. Two yielded -2. 12 -1. Huh. Did I make a mistake plugging in -3? -3 plus 3 is 0. 5 to the 0 power is 1. 1 minus 1 is 0. 0 over 2. No, that seems right. Did I make a mistake somewhere else? Oh, negatives. That's my mistake. So this should be here and here. There we go. Sorry about that. And so we've got a function that looks like that. And it's going to cross the x-axis way down there. And over here, we've got a function that looks like, let's see, -5, 12/25. -4, -2/5. -3, 0. -2, 2. -1. We'll be way up at 12. It's not going to get to 0 all the way until 62. So like that. Again, we're seeing symmetry across the line y equals x. Here is f of x, a logarithmic function. Log base 5 of 2x plus 1 minus 3. And over here, f inverse equal to 5 to the x plus 3 minus 1 over 2. In both of these, we've got asymptotes. Here we've got a horizontal asymptote at y equals -1/2. And here I've got a vertical asymptote at x equals 1/2. Sorry, -1/2. Domain and range of each. Domain, let's start with on f of x. Domain is the set of values x such that x is greater than -1/2. And we have a range, the set of values y such that y equals all reals. On its inverse, the domain is the set values x such that x equals all reals, and its range is the set of values y such that y is greater than -1/2. Any questions on my made-up example problem? Okay. Sorry about the error with the negatives at the beginning. Fraction -1, clearly negative. Do we want to move on in the review session from the textbook? I know Jasmine and Samantha both said that they would like to at least see the answers. I'm happy to just show the answers if we don't need me to go over them, and then we can pick which ones to go over. Oh, here's some input. Silence is astounding. I could go through 12. Let's go through 12. Let's do it. 12 has f of x equal to root x minus 3 and g of x equal to 3 over x. And our task is to find f composed with g, to find g composed with f, to find f composed with f, and g composed with g. So f composed with g, again, what that means is we take g of x and plug it into f. So that's going to mean I start writing f of x, and as soon as I get to an x, I write a 3 of x, 3 over x instead of an x. Sweet. That looks good. In g of f, I start writing g, but as soon as I get to an x, I write f of x. In f of f, I start writing f, but as soon as I get to an x, I write f again. X minus 3 minus 3. And in g of g, 3 over 3 over x. So all of those are reasonably acceptable forms. Each one we could clean it up a little bit. So if we decided we wanted to clean it up, on this first one, I might say, okay, I don't really like having fractions inside my radical sign. That's not super solid form. But let's see, what can we do about that? So we can say this is the same as the square root of 3 over x minus 3x over x, which is the same as the square root of 3 minus 3x over x, which is the same as the square root of 3 minus 3x over the square root of x. And if I then want to get a radical out of the denominator, I can say times root x over root x, which is equal to the square root of 3x minus 3x squared all over x, which would be a totally solid form. Going back over here, again, if I maybe want to get the radical out of the denominator, I could say times root x minus 3 over root x minus 3. Now I'm looking at 3 root x minus 3 over x minus 3. That looks good. And maybe I don't like having a compound fraction. So I say this is equal to 3 times x over 3. Oh, and look at that one actually cleans up. It's its own inverse. Sweet. And then you're supposed to state the domain of each, if I remember correctly. State the domain of each composite function. So first of all, we have to think about what's the domain of f and what's the domain of g. So domain here is x such that x is greater than or equal to 3. Yes? If I plug in 3 minus 3, that's 0. I can take the square root of 0. 4 minus 3 is 1. I can take the square root of 1. And g of x over here, the domain is the set of values x such that x does not equal 3. Oh, sorry, 0. 0, because you can't divide 3 by 0. Okay, so now we're set up to think about each of these individual domains. So for f of g, I know I need to plug things into g first. So if it's not in the domain of g, then it can't work. So already I know I can't use 0. Then I need to think about, all right, let's look at the whole function, f of g of x. So I know I can't use division by 0. Still doesn't work here. That's bad. Also, I know that I can't square root values that are negative. So I could do, if it was 3 over 1, that would be 3. 3 minus 3 is 0. So x equals 1 is good. And if I get larger than 1, like 2, that'll be bad. So 3 over 3 would be 1. 1 minus 3 is negative 2. Can't do that. So x has to be larger than 0. If it's negative, if x is negative, I'm going to do a negative minus negative. That's no good. So 0 less than x less than or equal to 1 is my domain there. Then my domain on G composed with F. Let's see. I know I'm plugging things into F first, so I need to have values greater than or equal to 3, at least. And I also can't have 3 because 3 minus 3 would be 0. So I'll say values of x such that x is greater than 3, but not equal to it. Because if I plugged in 3, 3 minus 3 is 0, can't divide by 0. On f of f, the domain is going to be the same as the domain of f. X greater than or equal to 3. 3 minus 3 is 0. Oh, nope, 0 minus 3 would equal negative 3. Can't do that. So let's see. I need root of x minus 3 to be greater than 3. So let's do a little bit of math now. Let's back up. I know that root of x minus 3 has to be greater than 3. So x minus 3 needs to be greater than 9. So x needs to be greater than 12. So we've got domain x, set of values x, such that x is greater than or equal to 12. Because 12 minus 3 is 9, square root of 9 is 3, 3 minus 3 is 0, square root of 0 is 0. As long as we're bigger than that, we're good. Okay, g of g. You can see that the output function is just x. But because the domain of g of x was x such that x does not equal 0, we know that the domain here on g of g cannot have values that are not within the domain of g. So it's going to be the same as the domain of g, x such that x does not equal 0. Questions on 12? If you really want to see that nicely cleaned up f of g, took a little bit of extra space. Okay. Any particular input on where to next? Shall I go ahead and maybe just show the answers to the review questions I gave, the review assignment I gave? So if you got something wrong, you can ask about it. Would that be useful? I'm going to go ahead and try it. If it's a bad idea, let me know. Oh, Rebecca says, can I do 14? Yeah, we'll leave that there and do 14. Okay, 14. Verify the function is 1-to-1, and B, find the inverse of the given function. So our function is the set including -1, 4, 0, 2, 1, 5, 3, 7. Okay, so let's see. I first have to verify that it's 1-to-1. Okay, my domain is the set including -1, 0, 1, and 3. My range is the set including 4, 2, 5, and 7. So -1 to 4, 0 to 2, 1 to 5, 3 to 7. Would you say yes? Verified? It is 1 to 1? I would agree. For every one input, there's exactly one output. For every one output, there's exactly one input. 1 to 1. Both the function and its inverse will be functions. It passes both the horizontal and vertical line tests. How exciting! Now for the inverse. The inverse function. Oh, this was A, for those of you keeping track. A and B. The inverse would be the set, including 4, -1, 2, 0, 5, 1, and 7, 3. Ta-da! We know that to find the inverse of a function, we merely flip the domain range. So I've replaced the entire range with the entire domain. Instead of -1, 4, I now have 4, -1. Instead of 0, 2, I now have 2, 0. Instead of 1, 5, I now have 5, 1. Instead of 3, 7, I now have 7, 3. Questions? Okay. If there aren't questions, oh, can I do 40? Jasmine says 40. 40 sounds like a great one to do. Number 40. Number 40 says, take log base 2 of a squared root of b all raised to the 4th and write the expression as the sum and or difference of logarithms express powers as factors. So this is just like we were doing on that worksheet. We're kind of just applying the properties of logarithms. So we know that a power can become a factor. So for log base 2 of a squared root b is my first step. Then I know that a product can become a sum. So I've got 4 times log base 2 of a squared plus log base 2 of root b, which I will then distribute into 4 log base 2 of a squared plus 4 log base 2 of root b. Okay, now I know again that exponents can become factors, so I have 8 log base 2 of a plus 4 log base 2, and let's go ahead and write this as an exponent so it's easier to see. A plus 2 log base 2 of b. Ta-da! Any questions on 40 or any others you'd like me to do specifically before I show you all the answers from the review problem set? Okay, maybe not. Wonderful. Let's go ahead and look at the answers. Oh, could I do 62? Of course I could do 62. Let's do it. 62. Ooh, and we get an A through F. How exciting. So I'm going to go ahead and take a picture rather than write that all down. New photo. And there's the instructions. And here is our function. Okay, so let's see. What are we supposed to do? Find the domain of F. A. Domain of F is going to be the set of numbers x such that x is greater than 0, which is the natural domain of the logarithmic function. And here, certainly still is true. If I had x equals 0, 2 times 0 is 0, I cannot do the natural log of 0. Neither can I do the natural log of any negative numbers. Okay. B. Graph it. Okay, so a general strategy for graphing logarithmic functions is to rewrite them as exponential functions. So I know that in this case, y equals 3 plus ln of 2x. So I'm going to solve for x. I've got y minus 3 equals ln of 2x. I can then say 2x to the y. Oh, sorry. No. 2x equals e to the y minus 3 power. And x would equal e to the y minus 3 power all over 2. Okay, now I need a table of values if I'm going to make a graph. So I'm going to say x and y. I'm going to plug in y's. The y values that I will plug in will be -5, -4, -3, -2, -1, and 0. Let's see. I need a scientific calculator to do so. I'm going to go ahead and pull up Desmos just to use it as a scientific calculator. Not that I would be graphing with it necessarily. You might need to be able to do this without graphing calculator. But I still want to be able to plug in these values. So I'm going to say e to the -5 minus 3 all divided by 2, which is point. Oh, this was a terrible plan. I don't want to do those. My bad. Let's do +5, +4, +3, +2, +1, and 0. My fault. So I guess gives me 3.69. When I try 4, that's going to give me 1.36. When I try 3, that's going to give me 1/2. When I try 2, it's going to be 0.18. And with 1, 0.068. We'll call it 0.07. And with 0, 0.02. Okay, now I've gotten x, y table. I would need to be able to sketch a graph. Let's do a nicer graph this time around. Okay. Some graph paper. An x-axis. A y-axis. Not necessarily in that order. We have 3.695. So 1, 2, 3.69 up 5. And I'll do, this is going to be in blue. And then 1.364, 1.364, and then 0.53, and then 0.18 up 2, and then 0.07 up 1, and then 0.02 up 0. 0.020. Okay, so we are asymptotic against x equals 0, and going up that way. There's f of x equal to 3 plus ln of 2x. Then, okay, check, check. Determine the range, any asymptotes of f. So, C. We've got range is going to be the set y such that y is equal to all reals. The range of any logarithmic function is the set y such that y equals all reals. And any asymptotes? Well, the asymptotes we should have known when we got the domain, but they are, the only one is at x equals 0. D. Find f inverse. Oh, I already did that. Lucky me. F inverse of x is equal to e to the x minus 3 over 2. Cool. Use f inverse to find the range of f again. Okay, well, we're going to say the range of f would be the domain of f inverse. So on E, range is still set y such that y equals all real numbers. When we're talking about f of x, and we know this to be true because the domain x such that x equals all reals of f inverse. So we're kind of just verifying. Use the inverse to find the range. Okay, so check and f, graph f inverse. You got it. So here's f inverse. It's going to be asymptotic with x equals, or sorry, y equals 0. I'm going to plot 5, 3.69, 5, 3.69, 4, 1.36, 3.5, 2.18, 1.07, and 0.02. So it's a function that goes like that. Kind of got ugly and squiggly at the end, but you get the picture. There is f inverse equal to e to the x minus 3 all over 2. Solid. Check, 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 check. Questions on number 62? Any others that you feel you'd like me to do by hand before I show you the answers to the whole problem set? Seeming like maybe no. Time to move on to this. So starting with number 4 was the first one I asked you to do. On number 4, you had f of x and root of 4 minus x. And you had to find f of g of 2, which was negative 5, g of f of negative 2, which was root 15, f of 4, which was negative 6,626, and g of negative 1, which was root of 4 minus root 5. After you were done with 4, you had to do number 12, which I've already done earlier in this review session, so I'll pass it for now. On number 14, I've already done that one. Number 18. Ooh, I did that one. Number 23, we did. Number 30, let's check it out. So the domain is x such that x is greater than negative 1/2. In other words, the set from negative 1/2 to infinity. That is the answer to number 30. On number 38, log base 2 of 2 to the root 3 should be root 3. Yes, there it is, root 3. Pretty basic application of the log of the property there. We have both an explicit property that we can apply there, log base a of a to the b equals b. Also, we can show that it's true by using the exponent rule and then knowing that log base 2 of 2 equals 1. Number 40. Number 40 I did. Number 62. 62, I just did that. Number 96, I have not looked at. Okay, 96. In 20 years, there'll be 7.204 grams, and in 40 years, 0.519 grams. That's number 96. Then some of you are 4th period, some of you are 6th period. 4th period folks have not gotten to see the answers to 99 to 101. 6th period folks have. Just in case there's any 4th period folks that come and watch it later or watching now, I'll show these answers now. 99, if you're in log mode in Desmos, you get 165.73 times 0.9951 to the x. After I'm done with these, Owen, I would be happy to do 96. On C, you get a graph. On D, it will take approximately 83 seconds for the probe to reach a temperature of 110 degrees Fahrenheit. And that was it. On number 100, you had to use a logarithmic regression. They use natural log. So 18.9028 minus 7.0963 ln of x was what they got. If you use base e, you didn't have to use base e. You could use other bases. That'd be fine. Then on C, you got a graph. And then you plug in x equals 23, and you get negative 3 degrees Fahrenheit. If you got a slightly different model and got slightly off of negative 3, that's fine. Not a problem. 101, you see the logistic relation. On B, you use a logistic model. It tells you 46.93 over 1 plus 21.273 e to the negative 0.7306 t. See, you sketch a graph, you see how it fits. D, you say, according to the function, a maximum about 47 people could catch the cold. In reality, we know that it's possible that all 50 people living in the small town might catch the cold. E, we find out that after 2.4 days, also known as the 10th hour on the third day, 10 people have caught the cold. Cool. Owen has asked me to do 96, which sounds like a good plan. Radioactive decay. Okay, so 96. The half-life of radioactive cobalt is 5.27 years. So that means every 5.27 years, an existing amount of cobalt decays unstable radioactive isotope, and it loses little portions of the neutrons. The neutrons basically just break apart, and the actual mass of the cobalt is lessened and lessened. So through that radioactive decay, you have less and less over time. And every 5.27 years, an existing amount of cobalt decays to half its mass. That's what that means. Certainly not part of the question. I'm just explaining it. If 100 grams of radioactive cobalt is present now, so we have Y equals an initial amount of 100, how much will be present in 20 years or in 40 years? So I'm going to write a rule based on what I know, that every 100 years, sorry, not 100 years. If 100 is left now, then half of it is going to be left every 5.27 years. So if I plug in 5.27, 5.27 over 5.27 would be 1. I would have half of the 100, or 50. If I plugged in twice 5.27, then this would equal 2. A half squared is a quarter. I would have gotten half of 50, and then half of that would be 25, so a quarter of the original 100. So this is a function that represents this relationship. And now I'm going to plug in 20 and plug in 40. So I'm going to go ahead and use Desmos. Hopefully that's okay. And I'm plugging in 100 times 1/2 to the x over 5.27. And if I want to, there's a graph. Hey, that's really nice. There's a graph of it decaying over time. It's less and less left. And I'm going to say, what happens if it's 20 years? Oh, that would be after 20 years. There is 7.204 grams after 40 years. Now I'm plugging in x equals 40. There's 0.52 grams. Of cobalt. Huh. It appears to be frozen, huh? And yeah, looks like frozen. I get the log mode. It's just me, the screen froze. I think the screen is frozen. That's what seems like it. Let's see. Go ahead and this, and don't save. New movie recording, and back to John Williams' iPad. No, Samantha, I never get tired of my classroom because my classroom is totally the coolest. But yes, it did freeze. Sorry about that. Where did I lose you guys? Did it make sense how I got this equation? Owen? All I did after that was plug it in, right? The 20 and the 40. But should I explain more about finding that equation that I found? Yes, I can tell you how to get into log mode on Desmos. Certainly I can do that. Should we do the one we had to use log mode? The CBL experiment? That's number 99. Did anyone have any more questions on 96? Sorry. Does 96 make sense? Okay, hopefully. So yeah, let's go all the way over to Desmos and check out the data from 99. So there's temperature in a portable heater, removing the probe, recording temperature over time. So new table, 0, 1, 12, 11, 13, 14, 15. And at time 0, 165.07. At time 1, 164.77. At time 2, 163.99. At time 3, we're at 163.22. At time 4, 162.82. Whoopsie. Time 3, 163.22. Time 4, 162.82. Second 5, 161.96. Second 6, 161.2. Second 7, 160.45. Second 8, 159.35. Second 9, 158.61. At 10, 157.89. At 11, 156.83. At 12, 156.11. At 13, 155.08. At 14, 4, and 153.72. So there's our data. Doesn't look very exponential, but we know it's Newton's law of cooling, so we know it must be exponential. So we're going to build an exponential model. So we're going to say, let's try y1 regressed against a times b to the x1. And right here, you ready for the big moment, Owen? To get into log mode, you notice this is slightly different than what the book gave you. To get into log mode, we tap log mode. And it gives us a slightly different answer. Rather than 165.71 and 0.99506, we hit log mode and we get 165.73 and 0.99505. Again, it is not necessary that you use log mode on your tests or quizzes, but if you want to be able to check your answers against the book is using log mode. Did that answer your question, Owen? Okay. Well, you've now seen all of the answers to all of the questions. Did anyone need me to go over any of the ones that I gave an answer to? Besides the ones I've already gone over? In that case, I think we'll call it an end at an hour and a half. Wonderful. We can all go to bed. Except for some of us are too excited for the steeplechase to probably even be able to sleep. It's so exciting tomorrow. That sound like the plan to you guys? Am I missing anything? You are welcome, Lauren. You are welcome, Owen. Lauren's excited for steeplechase. I knew it. You are welcome, Samantha. Okay, doke. You are welcome, Jasmine. Good night. Oh, no problem, Ryan. Of course. I will see you probably, unless you come in after school tomorrow, I will see you on Thursday for the test. Samantha's half excited. I will take half excited. Good enough. See ya.